Hey, what's up, guys? This is Cheng here again. So this time, let's take a look at one of the weekly contest problem, number 1658, minimum operations to reduce x to 0. Yeah, I think this is a pretty good problem, media level problem. Okay, so you're given like an integer array nums and an integer x. In one operations, you can either remove the leftmost or the rightmost element from the array nums and subtract its value from x. And note that this modifies the array for the future operation, right? And then it asks you to return the minimum number of operations to reduce x to exactly 0 if it's possible. Otherwise, return -1. All right, so one of the few examples here. So the first one, you're given like a number of this one. So here the optimum solution is to remove the last two elements to reduce to 0, which is this one. You remove 3 first, and then you remove 2. Then you got 5, right? So and another one is like this 2 here. So there's no way you can remove any. You can reduce this x to 0. So that's why you have -1. And for this 10 here, right? So you remove 3 first. You move this one, this one, this one, this one, and this one. That's total 10. That's why you have 5, right? And so here's some important constraints here. As you guys can see, the numbers of our x is 10 to the power of 9, and the number of length is 10 to the power of 5. Okay, I mean without the constraints, I think many people, most of us will start thinking about, okay, cool. So this is like, all right, return the minimum number of operations. Oh, cool. So we at each of the state we have two options. We can either remove the ones on the left, or we can remove the ones on the right, right? And then we can simply use the BFS, right? Let's just use BFS search. And then every time we can have a left and right pointer, right? I mean, anytime when we see the current, if the current one is not greater than x, we can remove it. We can either remove the left one or the right one, right? The and then by the time we have the current number is equal to x, right? And then or the current number becomes to 0, and then we have our final minimum numbers of operations. I mean, true, that will give you the correct answer, but it will TLE, right? It's because the BFS, right? So the BFS, the complexity for the BFS is the number of the states. And for this problem, if you want to use the BFS search, we will have like the current number, right? And then we have what? We have a left pointer, and then we have a right pointer. So this three thing will become the state of the BFS search. And this current number itself is 10 to the power of 9, right? And also the left and the right, this combination is also like a n, I think 10 to the power of 5, right? The length of numbers. So I mean this times this one, of course it will TLE. So with the given constraints, we cannot use the BFS. So then we have to find a better way to do that, right? Mm. So what's the other options? What are the options we have? Other options? I mean, we can try with minimum numbers, right? There's a DP, or there's what? Or there is like this maximum number of length, or the sliding window, right? A sliding window can also give us some minimum or the maximum result. And actually, so for you guys, next time when you guys see this the descriptions, you can either remove from the left or from the rightmost numbers. It will definitely become a sliding window problem. So why is that? Because because after removing some leftmost numbers and the rightmost numbers, what's left is definitely a what a sub array, right? We have a x here, and then we have some x removed from on the left side, and we have some x removed from the right side. So by the time we finish removing those numbers, and what's left is definitely a subarray, right? That's why, anything that relates to removing from the leftmost or the rightmost elements is actually a sliding window problem. And for all those problems, it can always be transformed to a what? Since we are for this problem, it's asking us to get the minimum number of numbers. Operations means the minimum numbers we can remove on both left side and right side. Actually, it's identical to what? It's identical to get the longest remaining subarray, right? Whose whose what? Whose sum is equal to the total minus x, which is this one, right? Because as long as we find the longest subarray whose like what whose sum is the is the is the total minus x, then in the end we simply use n minus that length, right? Will give us the answer we're looking for here, right? I mean, so since we have find that like we find that observations, right? We can start our coding here. So let's get our target first. The length is what? The length is let's get our target. So we have total. The total is the sum of the numbers, right? And then what's going to be our target? So the target is what? Is the total minus x, right? And then we'll have like this sliding window, right? To get the maximum, the longest subarray whose sum is the target. So the way we're doing it is we're using like sliding window where we have a left equals to 0, right? And the right equals to, sorry, right will be, we need the n here. So length is like the length of numbers. And now we have a longest, let's say a max length equals to -1, okay? Because we'll use this -1 to check if we ever find a valid candidate or not. So now we have a left pointer and then we have a right pointer, right? In range of n here. So with the sliding window logic, usually we have like it depends, right? It depends on for some problem, the size of a sliding window is fixed. And for some problem, it's not. I mean, especially for us, for this kind of problem, we're using a sliding window to help us find the longest, right? The the longest slide subarray. So which means that I mean the sliding window could be starting from 0, right? That's why we have to starting the right from the 0. And then for this kind of run sum problems, we always need to use like the running sum, right? So and every time when we add the new when we reach a new element, we increase the running sum with this right element, and then what? So and then we are updating our sliding window, right? We're making sure the sliding window is not greater than x. It's not greater than the target, right? Basically, this is what I mean. Right? Basically, while the running sum, right, is greater than the target, right? and the left is not greater than the right. Okay. Then we do a running sum minus the nums of left, right? And then we move the sliding window, the left pointer by 1. So by the time we're finishing this while loop here, now, right, we're up, shrink sliding window to make sure running sum is not greater than target, right? So now we have a valid sliding window, right? We just check. We check if the running sum is equal to the target, because we need this check, right? Because it could be the running sum is smaller than the target, right? And the uh, we only need the running sum when it's equal to the target, and then we can update our answer, which is the maximum length, right? Equals to the maximum, right? And the maximum length of right minus left plus 1, right? Yeah, so that, I mean, and after this sliding window for loop here, this max length will stores the maximum length whose target whose sum is the target, right? And since it's possible that the answer is -1, which means that there's no such subarray whose sum is the target, right? And then we just do what? We just return. We only return the n minus the longest, the max. So if its max sum is not equals to -1, right? Else -1. Yeah, thinks. Yeah, let's try to run the code here. Right, accepted. Cool. All right, so it's accepted. All right. I mean, just to recap the logic real quick here, So first, whenever you see the leftmost and rightmost element, right, remove the leftmost or rightmost element, and then this problem can always be converted to find uh, the answer for the remaining part, which is a subarray. And for this problem, the subarray we're looking for is the longest subarray whose sum is equal to the target, which is the total minus x, right? And and the way we're finding that longest subarray is using is to use the two sliding window approach, and every time when we add add the new location, right? We update, we increase the running sum, and then we check if the running sum is greater than x. If it is, we shrink it. Okay, we shrink it, and then we check if after shrinking if the running sum is the same as target, right? If it is, then we update the maximum length. If it's not, we simply skip that. And in the end, we just use this max length to get our final result. Yeah, and so the time and space complexity, right? I mean, as you guys can see, we have a sliding window, and for the sliding window, the time complexity is always O of n, right? And the space complexity is, do we have a space complexity? No. So the space complexity is O1. Yeah. Cool. I think that's it for this problem. Yeah, I believe if you want to solve it directly without transforming it to the longest subarray, I think there's also a way to do it, but I just find this is the most intuitive way to to solve this problem, you know. Cool. I hope you guys enjoy watching this video. Thank you so much, guys, and stay tuned. See you guys soon. Bye bye.